Many of the particles we've talked about up to this point you're familiar with. We've talked about protons and neutrons and electrons, the components that make up the atoms and elements we see on the periodic table. However, protons and neutrons are actually not fundamental particles. They're composed of smaller particles, particles called quarks, which we'll talk about in more detail in the next lecture. But the whole zoo of particles, we've talked about pions, gluons, we've talked a bit about photons, of course, light. So there are many, many particles that you've never heard of. The tau particle and so on, kaons and so on. So we're going to look at the general classification of particles. So there are hundreds of subatomic particles, but they all seem to have similarities in that we can plug them into different specifications, different categories. So hadrons are particles that can feel the nuclear strong force. So clearly, because protons want to push away from each other from the electromagnetic force, but an atomic nucleus like the helium atom, those two protons, while they want to push away, are bound together by the neutrons in that nucleus, the neutrons pulling on the protons via the nuclear strong force. Protons and neutrons both experience the nuclear strong force, therefore protons and neutrons are hadrons. They're not the only hadrons, but they are classified as what are called hadrons. As opposed to leptons, leptons are particles that cannot feel the nuclear strong force. For example, electrons and neutrinos. They cannot feel the nuclear strong force, therefore they are leptons. Other categories, bosons. Particles with zero or integer spin. So a photon, which has spin 0, is a boson. Compare that to fermions, which are particles with half-integer spin, like the electron. If you remember back to the lectures while we were building the atom, electrons had spin 1/2 or spin -1/2. They had spin up or spin down. Fermions are subject to the Pauli exclusion principle, stating that in an atom, fermions cannot have the same address, right? They cannot have the same energy state. And that's why the periodic table exists the way it does. The electrons can share orbitals only if they're unique address. The principal quantum number, magnetic spin, angular momentum, and the n, m sub l, m sub s, and s, those principal quantum numbers, cannot be the same for an electron in a given atom. So electrons are fermions, but they're also leptons. So just because you're in one category doesn't mean you can't be in other categories. Bosons, right, spin 0 particles. Photons can be bosons, but they're also not subject to the nuclear strong force, so they can be considered leptons. The four major categories we're talking about here, almost all the particles, subatomic particles, fit into at least one of these four categories. Now, hadrons, leptons, bosons, fermions, they all explain normal matter, the matter that you and I are made up of, and the particles that we can create in a particle accelerator. But some nuclear reactions and some natural or forced nuclear reactions or particle collisions can create what's called antimatter. For example, if you go back to how the sun generates power, the pp chain, one of the things created in the first step when two protons combine to form heavy hydrogen or deuterium, which has a proton and a neutron, that positive charge goes somewhere and it goes into what's called a positron. That is antimatter. It's an antimatter electron. What is antimatter? It's rather interesting. Antimatter is the same as normal matter in every conceivable way that we can detect so far, except it has a different charge. So an anti-electron or a positron has the same mass as an electron, same spin as an electron, but has a charge of +1 e instead of -1 e. An antiproton has the same the same mass as a proton, same spin as a proton, but has a charge of -1 instead of 1. Now, an antineutron is interesting. An antineutron actually still has charge 0, but the things that make up the neutron, remember neutron is not a fundamental particle, inside the neutron are little charged quarks, and we'll talk about quarks in a moment. And in an anti-neutron, they use the anti-particle, anti-quark inside that neutron. So if you replaced all of the matter in the universe right now with its antimatter equivalent, the universe, we think, with the Standard Model, would probably continue on very much the way it is right now. An anti-hydrogen gives the same spectrum as a hydrogen. An antihydrogen is just a hydrogen made with an antiproton and a positron going around it. If you could magically just change the charge in the universe by snapping your fingers, chances are it really would look very much the same. So why is there so little antimatter in the universe? That's actually a question that astronomers and astrophysics, talking about the Big Bang when matter was created, why this imbalance between matter and antimatter occurred, there's no good explanation for it yet. Hopefully physics in the future will explain why for every million or billion particles of regular matter, there's a single antimatter particle that was created during the Big Bang. However, we can create antimatter in particle accelerators and use that antimatter in these energetic collisions to create these exotic new particles and to study these exotic new particles. And the most interesting particles that we've detected in not necessarily recent history, but in the last 100 years, is the quark. And the quark we'll talk about next is actually what makes hadrons. It makes protons and neutrons and other types of particles, depending on how you combine these smaller subatomic fundamental particles called quarks. Now, when dealing with these particle interactions, it's important to note that a particle just can't decay into any other particle. There are rules, like with chemical reactions. You only can have a certain set of possible reactions depending on some conservation principles. For example, conservation of the number of electrons, conservation of charge on both sides, conservation of the hydrogens and oxygens and so on. They can't just magically vanish. You have to balance these equations. In particle physics, there are conservation laws as well, and we'll talk about a few big ones. First is, of course, conservation of charge. Charge cannot just appear out of nowhere unbalanced. So, in the reaction where a high-energy gamma ray, photon of light, high-energy gamma ray, can spontaneously decay into an electron and a positron. So, you take energy and you create matter, and that matter flies away, so there's a little bit of kinetic energy that goes away with it, potentially as well. But note how the charge is conserved. On the left side of the equation here, on the left side of the reaction, we have no charge. A photon has zero charge. On the right-hand side, we have a negatively charged electron and a positively charged positron. Adding those charges together, the net charge on the right-hand side of that reaction is also zero. So charge is conserved in this reaction. Electron family number must be conserved. Now, electron family number, there are two members of the electron family. There's the electron, not surprisingly, and there's what's called the electron neutrino. Neutrino is a small neutral particle associated with reactions with the electron. Now, family number, every time you see an electron or an electron neutrino, you add 1 to the family number. If it's not an electron or an electron neutrino, they have electron family number 0. If it's an antiparticle, if it's a positron or an antimatter electron neutrino, then it has a electron family number of -1. So electrons, electron neutrinos, +1. The antimatter equivalent, -1. Every other particle, 0. So on the left-hand side of this reaction, we have a muon. A muon is not in the electron family. It's its own family, which we'll talk about in a bit. So the electron family number here is 0. On the right-hand side of this reaction, we have an electron. So the electron family number is +1. We have an antimatter with a bar above it means it's antimatter. Neutrino, that nu is for neutrino. The subscript E means it's an electron neutrino. Since it's an electron neutrino, it's antimatter, it has a electron family number of -1. And here's a muon neutrino, which has an electron family number of 0. When you add plus 1 and minus 1 here, you get 0 on the right-hand side, which is the same as the electron family number on the left-hand side, so the electron family number is conserved. Note also, charge is conserved. We talked about that previously. This mu1 is negatively charged, this electron is negatively charged, so there's a charge of minus 1 on the left-hand side, there's a charge of minus 1 on the right-hand side, because neutrinos mean little neutral 1, neutrinos are chargeless. So this has charge 0, this has charge 0. So charge balances as well. Like electron family numbers, there's a thing called a muon family number. Muon family number is if you are a muon or a muon neutrino, you have a muon family number of plus 1. If you are an anti-muon or an anti-muon neutrino, you have a muon family number of minus 1. Things that aren't muons don't have a muon family number. So this is called a tau particle. It has muon family number 0. It's not a muon. This is a muon. It has a family member plus 1. This is an anti-muon neutrino. This has a muon family number of minus 1. This is a tau neutrino. It has a muon family number of 0. It's not a muon. So here is 0 on the left-hand side. 1 plus and minus 1 on the right-hand side is 0. So muon family number remains constant. So these reactions are possible because they don't violate these conservation laws. Reactions that violate these conservation laws can't happen. You cannot have a gamma ray, for instance, decay into 2 electrons. It's the same amount of energy because the electron has the same mass as a positron, but that would violate conservation of charge. So reactions that violate these conservation laws aren't seen in nature because they can't happen. Now, you can have, your book talks a little bit about conservation of baryon number, and again, we talked about what baryons were in the previous video, or what hadrons, I should say, were in the previous video. A baryon is just a hadron that decays into another baryon. So it's a hadron that decays into basically another hadron. Mesons are hadrons that decay into leptons, not hadrons, and leaves no baryons behind. So you have baryon and meson are 2 types of hadrons. Baryons number has to be conserved. So if you have a baryon in a reaction on the left-hand side, you have to have the same number of baryons on the right-hand side. Mesons are not conserved. Because if you have a meson as a hadron on the left-hand side, that will decay into leptons, so that number, meson, disappears. It's no longer a meson. It is not conserved. And then finally, your book talks a little bit about this, and we'll talk about it when we get to quarks in the next video. Strangeness is a quantum number that is conserved by the nuclear strong force, but not the nuclear weak force. So the argument is, if a reaction doesn't violate these conservation laws, it should be seen in nature, right? If you have all these conservation laws, but you come up with a reaction that should happen but doesn't, it leads physicists to wonder, why doesn't this reaction occur? A reaction, hey, this reaction doesn't violate conservation of charge, it doesn't violate conservation of electron family number, muon family number, baryon number, and so on. But you still don't see these reactions in nature. And the question is, why? So finally, they came up with another quantum number, which they called strangeness, odd name, but strangeness is a quantum number that also must be conserved in reactions dealing with the nuclear strong force. So particles are assigned a strangeness number, and that strangeness number has to be conserved before and after the reaction for reactions dealing with the nuclear strong force. If strangeness is not conserved, that reaction cannot go forward, even if it doesn't violate any of the other conservation laws. So that's an odd one. But we'll learn that the strangeness comes from the concept of what's called a strange quark, which we'll talk about in a moment.